I got here.
Yes.
I need some coffee. Oh damn, he's got it like it.
Thomas is not here.
Oh, there you go.
Yeah, well I know, but I'm gonna go and mirror it again, like we had it yesterday. Where's settings?
So Thomas thought the flagging was, so he unmirrored it.
Settings is down here next to Bluetooth.
Oh yeah. Yeah. So tell me where the displays is. Oh, okay, there it is. Yeah. All right.
Yes. Hi, Kevin.
Which way?
Paul, Kevin.
Which way is to this? Kevin, I would like the mirrored. Yeah, display. No, that's not the right one.
Yes, yes.
Show mirroring options on the. Oh, okay.
Okay, there you go.
There, that's much easier now. So, thanks. So I'm going to install the Google Drive. For some reason, when this happens on my desktop too, when we're asking everyone in the thing to wear a mask, yeah, just for the meeting, So yeah, for some this happens on my Institute laptop at home, but not on my home machine. So when I reboot it, I'm gonna have to speak to ITSC about this. The Google Drive breaks, and then I have to, which is like a box drive, but run by Google. And it happens on my Institute laptop as well. So I need you to sign in there. Thank you. And it doesn't happen on my home iMac, right? Yeah. So I don't know what is causing that. I'll just I'll mention his ITSD.
Is your Mac a little older?
No, it's running it. Well, it didn't happen on Big Sur. It didn't happen on Monterey. So I don't know why. If it's related to the. No, let's keep it because I may have to do this again. But this will probably fix the problem. See, there it is. There's Google Drive. Now it's happy. It's happy again.
Cool.
So it looks like it's happy again. Let me just go over here and double check. Bring up the Finder. Oh, that is it. That Finder.
Okay.
We have two down here. And,
See.
Yeah, they charge overnight.
Oh, okay. So I know yesterday. Yeah, actually.
Oh no. Okay.
The lapel or the? Yeah, one of them is a little funky. The other one, there's one that's I'll test it for you. No problem.
And I want to do tap. Let's see. Double click to keyboard trackpad. That's what I want. Tap to click. Sector. Back on click with 2 fingers. What about double click? Do they not do double click? Maybe not anymore. Point and click. So let's see. So maybe they don't do double click anymore.
Yeah, I'll grab it for you once we get set up.
So if I want to grab a window on this and move it, what do you do with if you don't want to press and do? Is there a way with fingers? Because there used to be, you could double click with a finger.
And then move it around.
Yeah.
That might be a setting that we have to initiate. It might probably changed in one of the updates or something. But
Click and then press from window. Used to be secondary click. See, it's on the clicks on the track, but it's not showing full and zone. More gestures. Swipe between pages. Swipe between full screen. I don't know.
more of a common
There's something I wanted to do. See, because then I clicked it. Let's see. No. Look. Oh, okay. It'll only let me grab up there now. Okay, that's it. No, I gotta use my thumb. All right. Yeah, and so I can my older laptop. I can double click like this, and then it'll grab. And I'll have to go look at what I have clicked and see, and maybe have a different setup. And maybe these more modern ones don't do that.
Maybe. Apple, they like to
Yeah.
change things every
Couple months. Was it a 3 thing? I mean, there must be a way. Oh no, that does that. 3 fingers does everything. Yeah, tap to click. Tap with one here. Tap to click. That's it. That should do it.
You hit that drop arrow right there.
What?
There's a drop arrow right here.
What do you mean?
On secondary click, there's a little arrow.
Oh yeah. Yeah, no. See, tap to click. Tap with one finger. That's what it's trying. That should do it, but it's not working. Tap to click. Yeah, it's not working. Anyway,
Are we? Okay.
The Google Drive is working.
Okay.
Almost nobody followed my name.
No, I noticed that. Sorry, Paul. All right, let's see.
Check. We'll leave these off for you. Check. Keep in mind that they take a second to boot up.
Yeah.
They're off now, but we can.
We have a separate person.
Oh,
What we did yesterday is we had the person.
check. 1, 2.
So Sultan
It
did
didn't
it.
happen very much.
No, Sultan did it, but that was it. Yeah, no.
Check. 1, 2. 1, 2. Buzzing.
Little
Yep.
buddies.
Okay.
Yeah.
Interesting.
Let's see, and this is the one with the. Is it on?
It's on.
Okay, so this is the one.
Yes.
Okay, cool.
Check. 1, 2. Hey, check. 1, 2. Check 2. 1, 2.
Not this one.
It's a little sensitive. Just don't call it names or anything. I'm just kidding. No, it has a little. It's one of the settings. It's like the high frequencies are a little too high.
Okay.
So I would keep it a little lower on the chest.
Okay, all right, that's good to know.
But other than that, it should be good. And you're good over here, I guess. Pick 'em up.
Hopefully, let's see. Find the first talk. No, yesterday it took a minute to actually open. All right, do I? All right, and then, so is this connected to Blue Jeans? Not yet.
Yes, it is.
Oh, it is.
Yep.
Okay, so we just need
So
to,
we just share screen.
when we want to, we can just share screen. Okay,
And
all
I
right,
just
that's
put
fine.
the camera there for now. Just
Oh, yeah, right. And then, yeah, so yesterday Thomas was, if people walk, he was doing that. Okay,
I got it.
thank you so much.
I'll be in
Awesome.
here for you guys.
Great. It's nice to have competent help. It really is.
Careful. which one.
Yeah. Oh, I know all too well, trust me.
And you're sharing the screen from down here, correct?
Yes, so we do have some, we'll go back and forth between online and in person.
They can just take the screen.
Yes. Yeah. Yep.
So we'll just need to share the screen when you're ready.
Okay.
Uh,
Yep. Yeah, probably in 5 minutes I'll go
Okay.
clap and get everybody to come in here.
Make sure I'll get the camera set up.
And the
But it was fun.
Okay, so we're in person. Oh, you remember? Wow. Okay. Yeah. So yeah, it would be good for you to get up there. Sure. Okay, sounds good. Thank you. Yeah, so you definitely want to get on a couple minutes.
Interrupt a little bit.
It's okay.
I'll try my best.
Oh, yeah.
Well, we have the. Okay, good.
People will need this is required. I didn't know why the house movement was so intense. Watching yesterday.
That's why I said they were.
Yeah, trying to.
Oh, okay.
Like during this. But that seems like the best way to go. I think in fact, maybe I should put that up. So people see it when they walk in. Yes, I updated it.
Oh, yeah, I was actually going to give them
This morning? Oh, no.
the tortoise. Sorry, you're talking about the moth.
Yeah. I thought.
No. I just
have that up.
okay, I thought the Charm City circulated.
I never leave it. If I go, if it's an opening, I would look.
Yeah.
Hi, Sarah.
I don't know.
Just reassure us about how to pronounce your last name. Okay, I was right. Isam. Other than that, no. Well, do you want to just check? I think we have your. Yeah, we have you up here. So. You don't have any movies, do you? Oops. Slideshow. Play from start? No, that's not what we want. Oops. Oh, we do. Oh, right. See, it looks totally different here because of those
Cookies? Cookies?
movies.
Yeah, well, the movies have sound.
Oh, no. They don't have that. Although there have been people who have tried to sonify.
Do you like this view?
I think this is fine, yeah.
Okay. And where's the lapel mic? Okay. Okay, I don't know if you want to play with it or.
I want to check if it
Thankful.
is working. Okay, great. Okay, it works. The movie works.
Good. I'm gonna repost this thing.
And behind your computer, I know you're hiding from us. Yeah, it worked pretty well. You're smart when you figure things like that.
Those are were moved. They were okay, so I just I sent the email.
So I get to go today
Yeah.
at 1:45.
Yeah, so I have got some. She said that
Two of us can go.
So in some cases, we have one more slot because group A don't have 5. So if anybody else can. Yeah, whatever. I noticed yesterday that people want to stick with the flash, so I just volunteer on.
Yeah. Like, if people know, they know.
Like this. But I use never so bad. It was like, it was like, yeah. Yeah. Well, I just moved there in January. Ah, yes. Oh, I get that.
I mean, yeah, that's a lot of snow. Yeah. But no, yeah. Yeah.
Exactly. I said it's not malaria. Oh, okay. Well, then also.
I know.
Right. What it just reminds me of a picture. No, I don't want to do that. Oh. Right. You can only change that screen.
Just tell everybody to have a look real quick.
Oh, all right.
And can we start that?
I don't know. Here.
We can view 100. Yeah. That's perfect.
Okay.
Perfect.
So if you're not sure whether you're having a mock tour today, how you can help. Group 3 is at 1 p.m. and group 4 is at 1:45.
Right. Okay, everybody see that? Because we're going to change this and get the talk up. Okay.
And good morning.
Okay, now how do I get this out of? I'm sure the desktop, right? Okay. Okay, and if you want, this. Oh, wait, get this out of the way. Yes. Oh, no, it does not. It goes left to right. Oh, it only goes left to right.
Put it on that side. Yeah.
This side? Okay.
There's text here.
Yeah.
No worries.
Okay.
Hi, everyone. Welcome. Can you hear me okay? All right. Thank you. So this morning is our supermassive black hole evolution session. And to start us off, we'll have Sarah Issaoum from the Smithsonian Astrophysical Observatory. So take it away, Sarah.
Thank you very much. Hi, everyone. So I'm an Einstein Fellow at the CFA. I'll be talking to you today about going from images to movies of black holes with the Next Generation Event Horizon Telescope. So you're probably familiar with our two most famous black holes, M87 and Sagittarius A star. We also image a number of other blazar sources and radio galaxies. The most recent one is the blazar J1924, which I had the pleasure to lead and just published the last month. There's another fun one coming up really soon on OJ287, which is a supermassive black hole binary. So this is kind of the short-term output of the EHT. You're welcome to ask me questions about this, but I won't be talking about the short-term results since I'm sure you've already heard quite a lot about it. I'll be talking about where we're going next in the next decade. So the Event Horizon Telescope is an array of radio dishes spanning the globe. We use a technique called very long baseline interferometry to do this, and we use the concept of aperture synthesis. So the Earth's rotation helps fill our virtual mirror, and we combine data on multiple temporal and spatial scales to get an image. So in order to build sensitivity the last decade to get the weak signal that forms the black hole shadow image, we had to expand to highly sensitive sites and very high recording bandwidths. So now that we're able to do this with high sensitivity, we're getting to the next challenge, which is how to make higher dynamic range images. So now we're currently coverage limited, and the next 10 years will be to build the coverage in order to make images that span a higher range of intensity. So this is the current EHT array, how it looks like in 2022. We have 11 telescopes at 9 geographical sites with various sensitivities. We're using really the most sensitive millimeter wave observatories in the world to form the EHT, but in the next decade, we want to expand this. So in the next 5 years, the NGHT concept phase 1 will add 5 additional dishes at different locations around the world and 345 gigahertz capability as opposed to our current 230 gigahertz capability to also enable multiple months of observing. So in this stage, we're having smaller dishes at different places in the Earth because the sensitivity is given by the current dishes, and the smaller dishes will increase the coverage. The phase 2 concept is going to be by 2030. So this is a total of 10 additional sites as opposed to current EHT, 345 gigahertz capability, and also multiple months of observing. So if you have a nice image of our famous M87 black hole and its jet, this is a simulation done by Andrew Chale, who is a previous Einstein Fellow, just graduated. This is what it looks like with the EHT in 2017. So you only see the brightest emission closest to the shadow. With the next generation EHT, we hope to make very clear images of the jet structure, which is much weaker because the jet is optically thin at this frequency, and then have the black hole shadow. And we can also make images across different epochs, across months of observing of M87, and therefore recreate movies of the dynamics of the jet and the shadow connected. So in the last year, I was sort of thinking about how do we make the NGHT more flexible in observing and enhance the science capabilities that we have at 230 and 345 gigahertz. What I was thinking about is, what about adding 86 gigahertz, which is a lower frequency where the jet is optically thicker, to connect more of the jet physics to the black hole? So we thought about these three questions. How does 86 enhance EHT science capabilities? What are the capabilities of standalone NGHT at 86 gigahertz with current or upcoming facilities? And how can NGHT at 86 gigahertz actually be used as a community instrument, not just for black hole shadow science? We did simulations with a reference array investigated by Alex Raymond and the team last year. These arrays were chosen just because they perform really well on these coverage metrics. So this is what we used for the simulations. We did weather studies for all these different sites, and we assumed a zenith opacity limit of about 0.5 to determine site dropout. And it turns out that none occur at 86 gigahertz, whereas some occur at the higher frequencies due to less good sites and lower sensitivity of the telescope. So at 86 gigahertz, actually full coverage with the entire array is guaranteed at any time of the year, which means at any time of the year you could observe with the NGHT at 86 gigahertz. We also made use of this amazing technique called frequency phase transfer. This was developed by Maria Rioja and Richard Dodson at the University of Western Australia. We've been working really closely with them on how to include that in the NGHT design. And it turns out that if you have simultaneous observations, the phase solutions from the atmosphere at 86 gigahertz, which varies slower, can actually be used to correct the tropospheric phase errors at 230 and 345 gigahertz. This actually makes the phases at the higher frequency smoother. We can integrate for longer, increase coherence time, increase sensitivity, and get detections at the higher frequencies in weather conditions where we might not normally on their own. So this actually significantly extends the time of year and weather conditions where we can observe at the higher frequencies if we add 86 gigahertz capability. So this actually did limit a little bit the frequency bands that needs to be integer multiples, but we found a really good plan for that that have been discussed also with the engineering team that is totally feasible to add 86 to 230 and 345. Another great technique that we made use of is multi-frequency imaging. So in this part, this was developed in the EHT imaging library, work led again by Andrew Chale, by regularizing a spectral index maps across frequencies. This allows us to connect the black hole shadow to the jet and outflow physics. So here are just 230 gigahertz images of the M87 black hole and its jet. On the left side, you will see just the NGHT stations. So these are the new sites only without the EHT array. So these are lower sensitivity telescopes, kind of very spread apart. You'll see that the image doesn't come out quite well. If you add the EHT, of course, you boost the sensitivity and the coverage, and you get really nice, black hole shadow and jet. So with the full NGHT array, you're able to do that. But if you make use of 86 gigahertz information simultaneously, you can make images combining the 86 gigahertz jet information, where the jet is optically thicker, to the 230 gigahertz sharper images of the shadow. And this is what you get. So just with the NGHT telescopes on their own, without the EHT facilities, you're able to make images of the black hole shadow and the jet. And so in this case, this was really a major breakthrough in that with the NGHT sites alone, without making use of the EHT facilities, which are designed to undergo their own science programs, we could actually observe and image the M87 shadow across various months with pretty good imaging fidelity. And then if you add 345, of course, you inherit the resolution from 345 gigahertz and capture higher resolution images. So there's a lot you can do with 86 gigahertz. Multi-frequency imaging helps us get spectral index and rotation measure maps to connect the shadow and the jet. You could do, if you had simultaneous observing, you could do time lag studies, core shift studies, looking at flares. You could do phase referencing and astrometry, which 86 gigahertz enables. You could do telescope calibration, so pointing and focus of your dishes is much easier at the lower frequency. When weather is bad at the higher frequencies, you could do long-term monitoring of sources because you can observe for longer during the year. And you can do transient science because this requires observing flexibility, and 86 gigahertz enables you to not just trigger at almost any time of the year, but also trigger a subset of the array with pretty good imaging fidelity. So how does NGHT fit with the next generation facilities? So you see that EHT is like this black bar here. NGHT, if you add 86 gigahertz with enable overlap with the next generation VLA, which is the big next radio facility coming up. Compared to the current and upcoming 86 gigahertz arrays, like the global millimeter VLBI array here and the next generation VLBI VLA here, the NGHT offers fuller coverage in long baseline range, so higher resolution and higher bandwidth recording capability, because the current GMVA is stuck at 4 gigabits per second, and NGHT is planning to record at 256 gigabits per second. So this is what GMVA and NGVLA coverage looks like, and this is what the NGHT looks like. So the entire observer year is available for 86 gigahertz science when 230 and 345 conditions are poor. But the NGHT sites on their own have excellent angular resolution but relatively poor sensitivity because they're weaker, smaller dishes. The NGVLA, on the other hand, has excellent sensitivity but relatively poor angular resolution because most of the stations are limited to the continental US. If you combine them together, you get the best of both worlds. You inherit the resolution from the NGHT and the sensitivity from the NGVLA. This actually enables us to do some pretty amazing things. So there are a lot of models of the M87 black hole and jet that predict that you could see a shadow of the black hole at 86 gigahertz if the jet is, if the accretion flow is optically thin enough. With the NGVLA, you wouldn't be able to do it because you don't have the resolution to capture the shadow. With the NGHT plus EHT, you would be able to do it. You would be able to see the shadow at 86 gigahertz and the jet. And if you combine all the arrays together, you will get amazing images, detailed images of the jet structure and the black hole shadow at 86 gigahertz. I think this is really exciting and offers a really amazing possibility to make black hole shadow and jet movies at 86 gigahertz through an entire observing year. So where are we going next? So last month, I had the pleasure to lead and organize the Broadening Horizons workshop, which connected theory, observation, and instrumentation surrounding 86 gigahertz and next generation EHT. The major question was to decide whether or not to add capability of 86 gigahertz to the array. The resounding answer at the end of that workshop was yes, and that we should really do it and that things should move forward. In November, we will have the first frequency phase transfer test from 86 to 230 gigahertz to have a proof of concept for this technique. This is scheduled with participating facilities, including the Korean VLBI network, which we're collaborating with. The KVN were the first ones to demonstrate that frequency phase transfer is feasible at lower frequencies, and this will be the first one at the higher frequencies for the NGHT. And then in May 2023, I have a proposal that was accepted in this ALMA cycle to do the first high bandwidth subarray observations with the GMVA and ALMA at 86 gigahertz. This will be observations of Sagittarius A star at high bandwidth, which will show what we can do with polarization and imaging if you have the sensitivity to observe at 86 gigahertz. Yeah, so this is where I end. Thank you very much.
Thanks for the great talk, Sarah. You ended exactly on time, extremely impressive. So questions for Sarah?
Nice talk. Is there any benefit to adding telescopes to the array on the other side of the planet, or because your baseline is already the size of the Earth, is it kind of diminishing returns at that point?
Yeah, that's a great question. So there are two things in which we would benefit from, well, there's one reason in which we would benefit from having telescopes on the other side of the planet is if we really want 24-hour observing. So this is particularly interesting in the case of fast time varying sources, especially Sagittarius A star, because this source varies very rapidly and it flares up. And if you want to look at a particularly flaring state, you'd want to catch multiple flares that happen. You do want to keep the observing going across the other half of the planet. But for most other sources, it really doesn't help because you reach the baseline, the resolution limit once you reach the size of the Earth. And the only way to get higher resolution is to go up in frequency. So Sagittarius A star is really the only case in which we would want that. And well, from a cost perspective, it doesn't seem quite worth it to add a whole half of the EHT on the other side just for this project.
Thank you, Sarah. I was wondering, this seems fantastic for imaging. Is there any possibility with the EHT and with these enhanced capabilities of also doing any kind of spectroscopy, or is that not a possibility? Because then you could measure motions and all kinds of other things.
Right. So previously, our frequency bands were designed so that we kick out all the lines that could possibly be at the frequencies, just because we're really focused on the continuum emission coming from the black holes. But there's actively a process to do spectral line, very long baseline interferometry with the EHT. So that's been building up, and there's a project trying to build that capability into ALMA. And ALMA is really the most sensitive site in the array. So once that's enabled in ALMA, it will make things a lot easier to do spectral line for the EHT. I think it would still remain mostly an imaging experiment just because VLBI is inherently about imaging. But if people are interested in looking at specific line widths across different baseline lengths and resolution, I think that is definitely a great experiment to do.
Sarah, any online? Not sure if someone's monitoring.
Yeah, I'm keeping an eye on it. There doesn't seem to be any questions so far online.
Well, thank you. All right, well, let's thank Sarah again.
Thank you.
So do I just need to let Maya go to stop sharing? Okay. This. Okay, so our next speaker is Maya Fischbach from Northwestern. So Maya, if you want to share your screen and take it away, you can go ahead. I think it looks fine.
Okay, yeah, you can see and hear me.
And just so you know, I'll give you like a 2-minute warning. So I'm going to interrupt you. I apologize in advance.
Okay, sounds good. Yeah, so hi everyone. I'm Maya Fischbach. I'm currently in the last couple months of my Einstein Fellowship at Northwestern University before I moved to CETA. And today I'll be continuing the black hole theme, but talking about different black holes, LIGO, Virgo, and Cagra's black holes, and I'll be addressing the question of, are these black holes made from smaller black holes? And this is work from a few papers that I worked on with the collaborators listed here, who are all wonderful people. Okay, so I'll start with just a brief introduction to these black holes and how they're detected. So we have this great observatory that is actually a network of gravitational wave detectors, the 2 LIGO detectors in the US, Virgo in Italy, Cagra in Japan, and later this decade, LIGO India will also join the network. And so these gravitational wave detectors are observing black holes from across the universe. And when we observe these black holes and a few neutron stars, we observe them in these binary mergers. So each gravitational wave event is represented here by these arrows in the stellar graveyard. And for each gravitational wave event, we have two component compact objects. The blue ones here are all black holes. And so we have these two component black holes that merge and form this final black hole. And one of the main things that we want to figure out is how those component black holes are made. Where do they come from? And so one kind of obvious possibility is that these black holes are remnants of massive stellar evolution. So you have this massive star that lives its life, collapses, and forms this black hole. And I'm going to refer to these as 1G or first generation black holes, the ones that are formed directly from stars. And then that black hole could encounter another 1G black hole, and then they merge and emit gravitational waves, and we detect them. But an alternative is that these black holes, these component black holes that we observe in a merger, are themselves formed from a previous merger. So you could have two first generation black holes that merge and then form the second generation or 2G black hole. And maybe that 2G black hole merges with another 2G black hole, and that's what we're observing in the gravitational wave event. Or maybe that 2G black hole merges with a 1G black hole, and we might observe some mergers like this. And so you can think of kind of these landscape. There are many different formation pathways that people have proposed for how these binary black holes might have formed. One class is these first generation mergers that just involve two 1G black holes. That can happen in binary stellar evolution. So there are several different subclasses of cases where you start off with the binary star system that evolves, leads to a binary black hole system that is then close enough to actually merge through gravitational radiation within the age of the universe. But you could also have black hole mergers happen in dense stellar environments where you don't necessarily start off with a binary star system. You start off in a system that has many more stars, such as a young star cluster, or a globular cluster, or an AGN disk. And that can have many stars that lead to many black holes that interact with each other dynamically, and that's how they assemble merging binary black holes. But those kinds of dynamical environments can also generally lead to hierarchical mergers. So that's these mergers involving 2G black holes, because you have a bunch of black holes around. So once those first generation black holes merge, that merger product might stay in this dense environment and find another black hole to merge with. So it's in these dense environments that can lead to dynamical assembly and the formation of these hierarchical mergers involving 2G black holes. And so one way that we can try to infer whether we're actually seeing these hierarchical mergers in our gravitational wave population is by looking at the spin. And the spin parameter that you often see in gravitational wave literature is this effective in-spiral spin, or chi-effective. And this is just often used in gravitational waves because it's well measured from the gravitational wave signal. It affects the frequency evolution of the gravitational wave. And it's defined as this mass-weighted average of the two black holes' spin components projected on the orbital angular momentum axis. So each black hole might be spinning those spin vectors here, chi1 and chi2, and then you take the projection on the orbital angular momentum axis of each one of those, and then just take the mass-weighted average, and that gives you this chi-effective. What this means is that if chi1 and chi2, these spins are preferentially aligned with the orbital angular momentum axis, this chi-effective will be positive. And if there's some preferential misalignment, they're tilted by more than 90 degrees, this chi-effective will be negative. And then if those spin tilts are isotropic, then chi-effective will be centered at 0 if these tilts are just random. And random tilts is what we expect from this assembly in dense stellar environments. So specifically for hierarchical mergers in these dense stellar environments, we can predict what the population distribution of chi-effective will be. And so that's what's shown in this plot. This is the PDF, the probability density function, and this is the cumulative density function, or CDF, in the bottom panel. And so if we have hierarchical mergers, we expect these to happen in dense environments. And so the chi-effective distribution will be centered at 0 and symmetric about 0. So that's what you see here in the PDF, and then in the CDF, 50% of the mergers will be less than 0 and 50% bigger than 0. But specifically for hierarchical mergers, this also leads to a robust prediction for what the spins of 2G black holes will be. So when you merge two black holes, that merger product, the black hole that's left over, will be spinning at a spin magnitude of around 0.7, and that really doesn't move around very much. And so that means that you're now, when you have a 2G plus 1G or a 2G plus 2G merger, you have one of your black holes with spin. It'll lead to your chi-effective distribution being pretty broad. So in the 1G plus 2G case is shown here in orange, and 2G plus 2G here in blue. And there are a bunch of other little curves here that are plotted, and those are changing the assumptions about what's the mass ratio of the merger, or what are the initial spins of your first generation black holes. Varying those assumptions really doesn't change what we predict for the final chi-effective distribution. So this is a pretty robust prediction just from any hierarchical mergers. You expect them to have a chi-effective distribution like this. And so it extends to fairly large positive and negative values, because these 2G black holes are always spinning at around 0.7. And so specifically, there's this robust prediction that around 16% of either 2G plus 2G or 1G plus 2G, it applies to both of them, 16% of these mergers will have a chi-effective that's more negative than negative 0.3. So that leads to kind of this very simple way of measuring the contribution from hierarchical mergers, because the hierarchical merger fraction, denoted here as FHM, is always going to be less than or equal to the fraction of black holes in your population that have chi-effective less than negative 0.3 divided by this 16%. And so this enables us to actually infer, based on the inference of the chi-effective distribution that we get from gravitational wave data, put this upper limit on the hierarchical merger contribution. And so, okay, thank you. So this plot here is showing the inferred cumulative distribution for two different phenomenological parametrized models for the chi-effective distribution. So the uncertainty you see here is because we have like 70 binary black holes going into this analysis. We don't perfectly know what this population distribution is, but we do know that regardless of the model, the majority of binary black holes have chi-effective greater than 0. And importantly, we haven't actually observed a single binary black hole that has chi-effective less than negative 0.3. And so kind of regardless of the model we pick, we always have this pretty small upper limit on what's the actual fraction of events in the underlying population with chi-effective less than negative 0.3. And so the punchline is that we can use this inferred fraction of events less than negative 0.3. So this plot here just takes this inferred distribution from this slide and plots it here as this one-dimensional distribution for these two different models. That fraction of systems that we infer that have chi-effective less than negative 0.3 leads to this upper limit on the hierarchical merger fraction. So even for this more conservative model, we infer that only 0.03 systems have chi-effective less than negative 0.3, which leads to this upper limit of around less than 20% of binary black holes must be hierarchical mergers. Just the final point is that you can also look at this fraction. It might vary with the primary mass of the black hole. So what we found is that it's possible that the hierarchical merger contribution is essentially 0 for all black hole masses, but it might be higher for the bigger black holes, which is kind of what you would expect. But still, even if you look at 50 solar masses, not all of the black holes at 50 solar masses can be hierarchical merger product. So if the alternative is stellar evolution must produce some black holes that are as high as 50 solar masses. And just to conclude, I'll leave up my summary slide, and I'm happy to take any questions.
Thank you so much, Maya. Any questions? Yes.
So Maya, the question I have is, there is some binary black hole mergers that occur in the field, and they may have chi-effective negative. How would you disentangle from these mergers in the clusters?
Yeah, that's a good question. So it's true when I showed, well, right, I guess, I don't know, it would be helpful to show here. But so I think what we can robustly say, we can say that the majority of binary black holes have positive chi-effective, and that means that we exclude a pure cluster origin because it's very hard in classical star clusters to break away from isotropy, to have any preference for positive or negative chi-effective. But it's true that some of the negative chi-effective systems that we observe, those might come from the field. I mean, it's very hard to make that happen because you do tend to preferentially align things if the binary has been together for a long time. And especially like the main way that people think you could misalign things is through some natal kick, but that would also tend to move the black holes further apart and make it harder for them to actually merge. So there probably isn't a large contribution from the field to negative chi-effective, but it might be there and it's not non-zero. So that particularly means that any limits that we put on dynamical origin or hierarchical mergers based on this negative chi-effective fraction is an upper limit because it might be contaminated with other formation channels. So this is all kind of just thinking about upper limits.
I think we can do one more quick question because we started a few minutes late, but I'm not seeing any. If there's nothing online, then I think we can thank Maya again. Thanks so much.
Thank you.
Nope, sorry, just kidding. Was there a question? Oh, sorry.
So would it be possible to use this to try to subtract out the hierarchical fraction to try to look at the initial mass function of black holes from the stellar mass formation?
Yes. Yeah, so that is a really interesting question. And this analysis is kind of too simple to do that, but there are some nice papers led by Chase Kimball, who's the second author here, who's a finishing grad student at Northwestern now, that do a kind of more thorough analysis that like simultaneously models the first generation binary black hole mass distribution and spin distribution, together with the possibility that some of those are forming the second generation ones, and kind of self-consistently models the population to get at the actual like stellar evolution black hole mass spectrum.
Thank you so much, Maya. One more round of applause and we'll move on to our next speaker.
Thank you.
Okay, our next speaker is Bart Ripperda from the Institute for Advanced Study.
Hi, thank you. Can you see my slides properly?
Yeah, it actually looks good.
Great. So I'll continue on black holes, and actually I'll try to explain a little bit on about how we model the kind of observations that Sarah was talking about and is planning for. Yeah, I'll talk mainly about flares. We have seen flares from a bunch of accreting black holes, low luminosity black holes, and in particular we have most information from Sagittarius A star and M87. Which are luckily also EHT targets. And for M87 specifically, we have seen bright TeV flares in sort of a quasi-periodic fashion, and particularly the ones in 2008 and 2010 were interesting because they showed a concurrent X-ray and radio flux coming from nearby the nucleus. So that posed the question, like, does the emission from those flares come from nearby the horizon of the black hole? Additionally, we know that the variability timescale is of the order of a few days, which by very simple causality arguments tells us that the emission region has to be small and has to be of the order of a Schwarzschild radius. So then a theorist would ask the question, does magnetic reconnection happen close to black hole horizons? And do we have a similar mechanism here as what explains flares from our own sun? Luckily from EHT observations and modeling, we know what the magnetic field structure is, so we can understand a little bit of whether magnetic reconnection is a feasible mechanism. And by looking at the polarization images from the EHT for M87, we can extract whether the global structure of the magnetic field is toroidal, radial, or vertical. And if you compare these toy simulations here with the actual image, you see that there is a strong vertical component in the magnetic field. And this was more or less predicted by Ramesh Narayan in about 2003 in a model that he called the magnetically arrested disk, where there is indeed in the inner region close to the horizon a vertical magnetic field, as you can see here, that can impede the accretion transiently. This was simulated with general relativistic magnetohydrodynamics by Sasha Tchaikovskoy in 2011. And indeed here you see in the blue you see a jet, in red and yellow you see an accretion disk, and here in the disk you see such a vertical magnetic field layer that can indeed halt the accretion for a certain period. We simulated this in 2D with a resistivity that allows for reconnection to occur at extreme resolutions. And what we actually saw is some new physics at the horizon. We saw that when the accretion is halted, actually a very thin layer of anti-parallel fields here forms at the horizon, at the base of the jet, which can reconnect, and in that way can liberate a lot of magnetic energy that is in the jet. And I'll show you with a cartoon how that works. So the idea is that the ram pressure of the gas is generally larger than the magnetic pressure, and the gas can bring in turbulent magnetic field here in the light blue lines onto the black hole. Those field lines fall through the horizon, but they're still connected to infinity, so they're being pushed into the jet. They strengthen the jet here in the white region, and at some point this jet becomes so strong that it completely suppresses the inflow funnel into a very thin layer. Well, the upper field line here is outgoing, the bottom field line is ingoing, so here you have anti-parallel field that is liable to break up and reconnect. And at this point, the ram pressure is about equal to the magnetic pressure, so this reconnection layer here, what it does actually it transforms this horizontal, radial, nearly horizontal field into vertical field that either falls onto the black hole or can escape. And if it escapes, as you can see from this great, my favorite Wikipedia image, if it escapes here on the right, it has a vertical component. And this is the vertical component that later on forms this barrier and actually can sort of self-sustain the reconnection for a certain period by stopping the accretion disk from destroying the reconnection layer. You see this also in local box simulations of reconnection, where you see that these little blobs filled with energetic plasma, they bring out this vertical magnetic field, and you see it here piling up at the edges of the box. So we had to do the largest 3D general relativistic MHD simulation to actually see this phenomenon in 3D. And you can see it here. And if you look at the bottom panel, you see that this is the magnetic flux that accumulates on the horizon. So the rising phase here is the accreting phase, where the gas brings in more and more magnetic flux until it reaches this point where magnetic pressure is equal to gas pressure. And then suddenly all that magnetic flux is quickly released. And that release happens in this layer here. And that is that reconnection layer that I was talking about. And during the release of that energy, a lot of magnetic energy from the jet is actually transformed into heat and kinetic energy in this current sheet. And that can power a flare. And in 3D in particular, as opposed to the earlier 2D that I showed, the period of the accretion, which would be a quiescent period, and the period of the flux decay match with observations of flare timing from Sagittarius A star, where we have most information. So if we zoom into this region, which we can do because of the high resolution, we see sort of what this looks like. And the takeaway from this simulation is that there is a transient non-axisymmetric reconnection layer, and the disk is indeed ejected. Here on the left, you see it's really ejected till 10 RG, and on the right, you see that the disk is slowly pushing back. And there are these tiny blobs, which we call plasmoids. They're typically filled with energetic particles. And we see that magnetic reconnection is actually essential in the duty cycle of accretion because it expels the flux, which can later on accrete again. So it's a redistribution mechanism for the magnetic flux. Resolving this mechanism required resolutions of about 5,000 by 2,500 by 2,500 cells, which is really extreme. It's about 1,000 times larger than our EHT simulations. And this was only possible with the GPU acceleration of the hammer code by Matthew Liska. Now, if you really want to understand this flare, you need to solve kinetic equations, Vlasov equation, Maxwell equation for the collisionless nature of the plasma, and then you can include the particle acceleration and the radiation that drives the flare. I want to show you a little bit more of the geometry. Like here on the left and the bottom, you see a 3D image of the quiescent phase of the accretion. And here, both the blue and the green field lines are in the accretion disk. They're both accreting onto the black hole. And you see that the temperature here, which is in terms of ion rest mass, it's all below 1. So this is all relativistically cold. Then we go to the flare state in the upper image, which lasts for a much shorter period. And now you see that the blue field lines, which are rendered at the same position, they're now being pushed away. So they're in the disk, and only a few of them can accrete over a small fraction of the azimuthal angle. Whereas most field lines here are now the green ones, which live in this hot plasma. You see now the temperature is everywhere above 1 in this layer, and this is the reconnection layer. So it's actually not a 2D feature, it's really a 3D spiraling current sheet. And if you zoom in, you see these little plasmoids, which are helical little flux tubes, and you see X points where really reconnection has just happened. So this purple field line here falls onto the black hole, and the green field line can escape, and you see it already acquired here a little vertical component which will grow when the tube expands outwards. And here both really all field components reconnect. So we call this no guide field reconnection, which is further not important for the story. So if we look at MED7, what would it look like during such a flux eruption phase? Here you see a video by He Jia, a PhD student in Princeton. And at some point you will see the flare. And it will maybe be a little bit counterintuitive, because maybe you think that when a flare occurs, the EHT radio image will become bright. But actually the radio image dims, as you can see here. So this is the period of the flare. And the dimming is because the accretion disk is ejected. And the accretion disk is typically what gives you the submillimeter. And then the reconnection layer that is sort of left in the inner 10 Schwarzschild radii is too hot to radiate much in the radio band. So the image will, we predict at least that the image will dim. And this gives us a nice opportunity to actually study the photon rings, which may imprint the nature of space-time, according to a series of recent papers by Michael Johnson and Sam Gralla, which we can very nicely see with this high-resolution GRMHD that we did. And in recent observations of Sagittarius A star with EHT, we may have seen this dimming, as we saw with ALMA that the radio flux went down when we saw an X-ray flare. But this is something to be further understood. We only have the light curves, and we didn't look at the images yet. So talking about Sagittarius, we of course also have those orbiting flares seen by the gravity interferometer. So gravity observed what they call the orbiting hotspot in the near-infrared non-thermal emission. And you see here on the right that there is a centroid motion of this flare. And the idea is also here that reconnection can form these plasmoids, these little blobs of energetic plasma with radiating electrons. And also here, the issue is that the electron gyro radius is very small compared to the object, and the emission region of the hotspot is about 1 Schwarzschild radius. So you have very large scale separation. You need very high resolution simulations to understand this. We can use the same simulation because MHD is dimensionless. So this is the same large 3D simulation as we showed before. Now you're seeing the temperature in a 2D cut. And what you saw here was that reconnection occurred. Let me see if I can go back a little bit. So reconnection is happening here. This is the same current sheet I was talking about before. You see it getting hot. Thank you. And what you see is that this current layer here is expelling this vertical field. I'll put a box around it. So this vertical field is now pushed outwards while the inner region is already accreting again. And you see that it's still hot. It's not as hot as the current sheet anymore. But what this is pair plasma that comes from the jet, is accelerated through the current sheet and pushed into the disk. And if you look at it from the top, you see it as a low density blob that actually orbits. And this aligns very well with what gravity saw. And it seems not to be a single plasmoid because a plasmoid has this helical field structure, but this exhaust of the reconnection filled with many plasmoids actually has a vertical field structure, which agrees with polarization measures of gravity. So Vladimir Zdankin, a postdoc at Flatiron Institute, is modeling this with particle and cell. As you can see here, still preliminary results, but then we can really understand the energization of particles in such a hotspot. This is my outlook. So next frontiers are to stop modeling with magnetohydrodynamics and actually start modeling individual particles. And Alisa Galishnikova at Princeton, also a PhD student, is modeling a 2D accretion flow onto a black hole with general relativistic particle and cell. And she's modeling electron, positron, ion plasmas. And here you see the ion content. And you see that once such a reconnection layer forms, that the ions really have zero density. So this is really pair plasma around the current sheet. And you see that there are ions here in the accreting disk, which is now pushed away. So we can model this with local box pair plasma simulations where we include fully dynamically synchrotron inverse Compton scattering and pair plasma production in such a current sheet. And this is being done by Heike Jacobian, postdoc at Princeton. And in this way we can become really quantitative and produce spectra from the simulations that show you components due to inverse Compton that can really produce TeV flares. Synchrotron components that can give you X-rays, both for Sagittarius and for M87, and lower energy components due to secondary synchrotron radiation. Thank you very much. I'll take questions.
All right, questions for Bart. And your video does look blurry, though I don't think we should really mess with it because we can still hear you. So just so you know.
Oh, I'm sorry about that.
Hi, so this is very cool. So I was wondering, how long does it last, the flare? Because you were saying that the disk is ejected and then it's an opportunity to see the photon ring. So I was wondering how much time would one have to measure the photon ring?
Yeah, so it's about 100 to 200 Rg over c, so Schwarzschild radii over speed of light. compared to an accretion period of 1500 to 2000 RG over C. So it's an order of magnitude less than the quiescent period. For M87, that would be a few days, and for Sagittarius A star, that would be of the order of minutes to about 1 hour maximum, I think. So, so in both cases, it should be possible. For Sagittarius, we'll have to have a high time cadence of the observation. For M87, we'll have to be lucky because that flare will only happen every so many years. So you'll have to be watching at the time the flare occurs. So in both cases, it will require some careful planning, but it's possible.
Okay, let's thank Bart again. Thanks so much.
Thank you.
Okay, our
sorry.
next...
Sorry, I did have a quick question about if we have time. Is that all right? Is there time?
Oh, yeah, you can go ahead. My bad.
Thank you. No, all good. I wanted to say thanks, Bart. That was really neat, and these simulations you're doing are awesome. I wanted to ask about the treatment of the black hole in the simulations and whether it's I'm assuming it's a static metric, but whether it's Schwarzschild or Kerr, and whether adding rotation would make any difference to the results.
Yeah, that's a great question. So it's of course static metric. We use Kerr, but we also did Schwarzschild. The thing is that for triggering this reconnection, it's important that you have an inner light surface and an ergosphere that are not at the horizon, because the reconnection seems to really be triggered at this inner light surface or at the ergosphere. So like for Kerr, it works better. And then the space-time rotation also adds some additional shear, which triggers the instability further. So for Kerr, it seems to be more violent and more promising. For Schwarzschild, we also see reconnection, but for example, much smaller plasmoids. So that is something that I'm trying to understand exactly. And I'm also trying to understand if we can link that to observations somehow, like if we really expect more violent flares for larger spin. But that is, yeah, for the future.
Great, thank you. Okay, if we don't have anything else, sorry for that awkwardness, Haley. Let's move on. Our next speaker is Fei Zhuang from the University of Arizona, so you can take it away.
Okay. Can you see my slides?
Yep, looks good.
Okay, thank you. So thanks everyone. I'm Fei Zhuang from the University of Arizona. I'm currently in the last month of my current fellowship, and today I really wanted to take this opportunity to thank everyone for the amazing support in the last 3 years. And today I will talk about the environment of the earliest supermassive black holes, like moving from the local universe to the very high redshift, deep into the epoch of realization. So before I talk about the environment of the earliest supermassive black holes, I wanted to briefly summarize what I talked before. Like in 2020, I presented the discoveries, how to discover and study the earliest supermassive black holes by using like wide field imaging surveys and to study the black holes in the center. And in last year, I moved to like a slightly larger scale to talk about the quasar host galaxies by studying the quasar host galaxy morphology, schematics, and whether the black hole co-involves with the quasar host galaxies. So this year, I wanted to move to a much larger scale, wanted to connect whether the supermassive black holes like connect with the megaparsec scale environment. So here I saw to cut out of the simulation, cosmological simulations. In the left part, we saw average density region in the universe, and in the right part I saw overdense density region in the universe. So from those black dots in the simulation are basically indicating the location of the black holes, with the big dots means bigger black hole. And you can see that the 10 billion, the billion solar mass black holes, like with the biggest black dots, can only be found in the overdense region, which means the supermassive black holes at redshift 6 with mass like more massive than 10 to 9 solar masses also can only be found in the most massive dark matter halos and surrounded by the most density region. And you can see like overdensity of star-forming galaxies. But this is from the simulation side. Is this real or not? So we needed to prove this from the observational perspective. I'm not the first one to study this problem, but actually this problem has been investigated for about 2 decades since the discovery of the first redshift 6 quasars. and using both ground-based observations and the Hubble Space Telescope. Here I show some examples of the Hubble Space Telescope observations. You can see that just all the highlighted by the red colors means people find the overdensities of star-forming galaxies in the quasar fields, while the blue point, the blue highlighted target shows no overdensity. So this is confusing because, like, based on simulation, the black holes, the massive black holes, can only be found in the overdense regions. But why some of them shows overdensity of galaxies, but some of them do not show overdensities? So one possible reason is that the HST field is too small, cannot cover the whole, like, 10 to several tens megaparsec scale. But people also tried to do this with ground-based observation to go like a wider area, but slightly cellular depths. But again, people found like some quasars reside in the massive reside in the overdensity of galaxies, but some of them does not. So that seems like didn't solve our confusing. Until recently, people try to like. First, I wanted to summarize all these observations are based on the broadband imaging selection. Basically, you are using photometric recipe to select galaxies. But in order to figure out whether those galaxies are really physically associated to the quasars, and you need to spectroscopy. So until recently, people have tried to do spectroscopy on some of the overdensity field. And finally, people found one overdensity of galaxies surrounding the redshift 6 quasar, as shown here. All the blue color shows the galaxies with spectroscopic redshift, and here also shows 2 λ5 meters at quasar redshift. So this is the first spectroscopically confirmed large-scale overdensity. However, like trying to do the broadband imaging and then follow up with the spectroscopy is really expensive. Like currently, only few such quasar fields have been observed. So as a summary here, I wanted to like why it's so difficult to investigate this problem. First, I have already mentioned that the HST field view is super tiny. It's too small to cover the whole whole structure. And also, most of the observations previously are using the so-called Lyman break, the broadband imaging dropout technique to select the Lyman break galaxies. Well, the Lyman break galaxy selection using field broadband has a really large uncertainty on the redshift of the galaxies. Like the signal can be washed out by really large projection effect. And also, using the rest frame UV broadband imaging, it's not sensitive to the obscure galaxies. So we missed a lot of galaxies. And also there are some cosmic variance when people try to study like individual objects. So how to solve this difficulty? This is what I have been doing in the past 2 years. And the first thing we can do is to switch the broadband to narrowband. So we can use the narrowband imaging to searching for like λ5 meters, because the narrowband imaging has a much narrow bandwidth and can like better constrain the redshift of the galaxies and to pick up the galaxy physically associated with quasars. And again, we can, for those narrowband selected imaging, we know it has emission line, so we can do the spectroscopy to identify the real redshift. And also we can do the multi-wavelength follow-up to including both obscure galaxies and unobscure galaxies. Finally, I wanted to build a large quasar sample and to like start statistically study this question and to measure the quasar galaxy cross-correlation function, and finally statistically resolve whether the quasar reside in the overdensities of galaxies and hosted by massive halos. So first of all, let's talk about how to do the narrowband imaging, why we wanted to do narrowband imaging. Here I show the sky transmission and also sky OH lines from ground. You can see that there is a small window here at about 9200 angstrom. So there is no sky OH lines, which means we can like target the Lambda alpha emission line at redshift 6.6 or so to go fairly deep because you do not have sky OH lines. And as such, we are doing a large sample of quasars, basically targeting about 15 quasars using the narrowband imaging from the Subaru and IMAX, which we made a new narrowband filter for IMAX. And also we are targeting redshift 6.7 quasar field using the HST to try go to a deeper region, but a slightly smaller field view. So here I wanted to show some preliminary results. And here is an example. We have observed 3 quasar fields with narrowband imaging, and we see overdensity of lemma 5 meter in both fields, in other fields. So here I show one example from the Subaru observations. And this is the quasar at redshift 6.6, and we observed with the Subaru deep IZ and narrowband imaging, and we also follow up with the spectroscopy and also ALMA observations. So in the right part, I show some cutout image of the selected lemma 5 meters. You can see that those galaxies are super bright in the narrowband, but very faint in the Z-band and undetected in the I-band, which means it's a really high redshift object. And also there is a missing line in the narrowband imaging, means it could be a high Z lemma 5 meter. So here I show the spatial distribution of those narrowband imaging selected lemma 5 meters. You can see each blue dot means lemma 5 meter candidates. And as you can see, like most of the lemma 5 meter candidates are actually concentrated to the central field. In the single Subaru field, we actually identify about 90 lemma 5 meters. This is a huge number. It's like the overdensity within the yellow box here is about 4 times larger than that estimate based on the outskirt of the field or the galaxy luminal function. So which means we are seeing an overdensity of lemma 5 meters. So to characterize whether this overdensity is associated to the quasar, we also performed a spectroscopy follow-up. And all those green dots here, so spectroscopically confirmed galaxies, which indicates like they do reside, those galaxies do associated with the quasar. And here I also show the overdensities of those galaxies, the surface density of galaxies as a function of magnitude. And you can see like all those black open squares or triangles or circles that indicate the blank field, and the red one shows the surface density of a galaxy in the outskirt of our field, but the solid red dots shows the surface density of galaxies in the inner part, which means we do see like the overdensity of galaxies in all different magnitudes. And here I show some examples of the spectroscopic redshifts, and both 2D and 1D spectra of those galaxies. We can see clearly lemma 5 missing lines, and like so in there, all those galaxies are at a redshift around 6.6, and which proves these galaxies are really associated to the quasar, like tracing a really large scale, large scale overdensity. And the overdensity in the central, like 1 or 2 megaparsec, is larger than 30, which is huge. And also the overdensity is about 4 within like 30 to 70 co-moving megaparsec. If like we assuming this structure will collapse into clusters in the local universe, it could have a mass of about 7 times 10 to 15 solar masses. It's like more massive than any clusters in the local universe. Here also shows the ALMA observation of this field, and you can see like this is a single ALMA pointing. We can see several galaxies in the field. And also there is one merger galaxy associated to the quasar. So all those some millimeter galaxies are also at quasar redshift, indicating this quasar really traces a large scale overdensity of both obscure galaxies and unobscured galaxies. And here I show the measured cumulative overdensity profile of this structure. You can see like the inner part is some millimeter galaxy, while the outer part is lemma 5 meter galaxies. Well, those different lines show the theoretical predictions for like quasar galaxy cross correlation or even protocluster. This line shows the average of the protoclusters at intermediate redshift or redshift 2 or 3. So you can see this structure is really has a really large overdensity and extends to a very large scale. And this is the largest overdensity of galaxies we see in the early universe, and the most massive one also. So this is this project. I also wanted to highlight there is another project that I'm pushing through. Is we call it ASPIRE, which is a spectroscopic survey of vast halos in the Renaissance era. So what we are doing is basically using the GWST near-cam imaging and the wide field slitless spectroscopy to do a redshift survey in 25 quasar fields. And we use the slitless is because we do not need to rely on any pre-selection of galaxies. We just pick up the O3 emission lines from galaxies and to see whether we can see an overdensity of galaxies in a large sample. And this program is also accompanied by many other observations. It's exciting that we got some GWST data in the last month. We are still working on the data reduction, but here I saw near-time imaging here. As you see, there are many galaxies, and the red square here highlights area that we will do ALMA mosaic, which is recently approved as a large program. It's approved for 100 hours to do the mosaic of 96 observations of all the 25 quasar fields to identify both like obscure galaxies and unobscure galaxies. So I would summarize here. I wanted to ask one question is, do quasar reside in the most massive halos and traced by galaxy overdensities? Previously, people mostly using the broadband imaging and gives inconclusive results. But now I wanted to try using both narrowband imaging and spectroscopy to do the very large scale overdensity around quasars, and we do find some already. And also we are using GWST and ALMA to study a large sample of quasars and try to solve this problem statistically. Okay, I will stop here, and thank you very much.
Okay, thanks so much, Big. We have time for a question or two very quickly.
Super interesting. Thank you. This is probably really premature, but I'm expecting that there's a higher fraction of galaxies with active accretion at high redshift. And so at some point you should start to see that, pairs of quasars, or, find nearby galaxies with enhanced activity relative to lower redshift. And I don't know if you have any thoughts about that, or when that might start to happen.
Yeah, that's a really interesting point. Actually, we have already seen quasar pairs at redshift 5 east, but not redshift 6 yet. It's probably because the density of quasar is so low. But in terms of the galaxies in the quasar field, I think we do see a large fraction of galaxy mergers in the quasar field. Like from the GWST imaging, we already see lots of mergers close to the quasar itself, and we are doing the spectroscopy, so we are still working on the data reduction, but we will soon have the results to see whether these galaxy mergers are associated to the quasar. And also from the ALMA observations, we will also target the semi-millimeter galaxies, which are more massive galaxies that we would expect to see more galaxy merger also. I think we will see such features very soon, maybe later this year or next year. And in addition to this, we also have deep Chandra observations, which we will try to, and also VLA observations, which we try to identify whether any of the galaxies in the field has AGN activity. Yeah, stay tuned. We will have some results later this year or next year.
Do we have anything quick online?
Yeah, we do have one question from Rowan. Would you like to unmute and ask it yourself, or I can go ahead?
Yeah, Figgy, this is a great talk. So one thing I worry about with these quasar-associated galaxies is, like you're saying, right? Like the merger fraction might be potentially higher. It's like an overdense environment. I was just curious, how much can we extrapolate the properties of these quasar-associated galaxies to the field galaxies? Because things like Lyman alpha are accessible to us only in these quasar bubbles, right? Like during the epoch of reionization and stuff. So yeah, just wondering if you thought about how much we can basically generalize from these quasar associated galaxies.
Yeah, that's an interesting question. We actually are studying the galaxies in the overdense region and compared to the blank field like cosmos or whatever blank field to study the difference of the galaxy properties is one of the key questions of our proposal. So actually, for now, we do already see difference. Like we already see enhanced Lyman alpha emission in some of the galaxies in quasar vicinity. We see this is probably because quasar ionized big bubble, so the Lyman alpha is easier to escape. We see double peaked Lyman alpha emitters in the quasar vicinity. And also, as I said, we currently do not have a large sample of galaxies yet, but we will have them soon with the GWST observations. Then we can compare other properties, like whether they have enhanced O3 emission or others, like star formation activities or other properties to compare. Yeah, this is really interesting, and I believe we will learn a lot about the galaxy evolution in like overdense regions and different from the field galaxies.
Yeah, super exciting. Thanks.
Okay, I think we should wrap it up. But let's thank Fig and all of our speakers from the great session. Thank you.
Okay, so we have a coffee break, but before everybody gets up, we have a couple of reminders. One, if you're giving a talk tomorrow and you still haven't uploaded your talk, please do so. We're missing 3 of them. 2, we will be doing a group picture for those of us that are here in person at the conclusion of the next session. So we'll have our coffee break, we'll come back here at noon, and then after the 4 talks, we will go out and take the picture, and then people that are going on the mock tours will go, and then everybody else will have lunch. And there was something else I was going to say, but I forgot what it was. So anyway, go enjoy your break, and we'll see everybody back here at noon Eastern.